The today topic is electromagnetic induction. So in the electromagnetic induction, first I will discuss about the Faraday law, and this experiment done 200 years ago by Faraday. So this experiment is you need one coil, closed coil is important point is it should be closed, and the coil connected to the galvanometer to measure the current. And now we need one bar magnet. I can see this is the south pole and north pole, and these are the magnetic fields which is passing through the coil. Now I am considering the case first when magnet position at rest, there is no motion. Then so magnetic field is a constant. There is no change in magnetic field. It means flux will also constant, and they observe current in the galvanometer is a 0. Second case, he took moves towards the coil, moves towards the coil. So it means magnetic field is a increase, flux is also increasing. Main point is a magnetic field is a changing. Okay, so the flux is also changing, and they observe current in the coil. Third, they again stop the bar magnet, then again they observe current in the galvanometer is 0. Fourth case, when moves away from the coil, then again they observe current in the coil, but that is in the different direction, minus I. Okay, so this experiment done by the Faraday. So the conclusion of this experiment is whenever the flux changes in the closed conducting loops through magnetic field, then EMF is produced in the loop. So what is the definition of the flux? So flux is a B dot dA. So you can write B dA cos theta, where theta is a angle between magnetic field and aerial vector. You can also write A B cos theta. Okay, so now take some example, because flux only can change first by changing magnetic field, second area of the loop, and the third angle between the theta. So with three we can only change the flux. So now see the one example here. Suppose that this is the closed loop we have in the plane, and magnetic lines are passing along the plane. So this is the direction of magnetic field, and aerial vector will be perpendicular to the plane, that will be the 90 degree with magnetic field. So the flux is a 0 because theta equal to 90 degree, with flux formula of flux equal to AB cos theta. Now the second case, if you have a same coil but direction of magnetic field is a cross or dot, like into the plane, then the flux will be AB cos 0 degree, depend actually either dot or, so the flux will be maximum. So the general formula of flux is, suppose that if you have magnetic field in this direction and aerial vector in this direction, so this you have to take angle theta. So the flux equal to AB cos theta. Here you can take magnetic field and area, sorry, in this, so 0 or you can pi, 0 or pi also. Okay. So the Faraday law you can write in the numerical term. So induced EMF is a change of flux. Minus sign is indicating because flux is changing. So d phi will always have positive value, and minus is showing you always induce EMF oppose the change. Oppose the change. So you can write current in the loop is a induced EMF by resistance. So minus 1 by R d phi by dt, where R is a resistance of coil. For N loop, suppose that if you have a N loop in the coil, so the current in the coil will be minus 1 by R N d phi by dt. What is the minus sign? Let's discuss about the direction of induced EMF, direction of current. So direction of induced current is given by Lenz also. So here I will discuss about Lenz law. So what is a Lenz law? So the direction of induced current is such that it opposes the changes that has induced it. So now let's understand with the case by case. So the first case is if suppose that flux is increased, then induced current will try to weaken or reduce the flux. So how to reduce the flux? Because as we have discussed about, if flux can only increase through the magnetic fields, area and theta. Okay, so the current will try to decrease the magnetic field. This is very important here. Second point, suppose that flux is decreasing. If flux will decrease, then induced current will increase the flux. Okay, so current always oppose the changes. That is important. So induced current will oppose the changes. Let's understand with some question. So the first example, suppose that if you have magnetic field into the plane, so this cross always will give the direction of magnetic field into the plane. Either you can write minus k, okay, and one closed coil moving with constant velocity v. So in this case you have to think about what is the induced current. So now you can see, because magnetic field is everywhere, uniform magnetic field is given, and area is also constant. So in this case flux is AB, okay, area is also constant, B is also constant. So flux is not changing. It means induced current will be 0 here. But in the same case, suppose that this loop is here, just entering into the magnetic field. So now in this case, when I enter into the magnetic field, uniform magnetic field, the flux will increase, because now we have magnetic field. Before there was no magnetic field, so flux was 0. So now it is going 0 to some definite value. So the flux is increasing. So flux will change. It means now we can see the current in this loop. Okay. So what is the direction of the current in this loop? So here flux is increasing. According to the Lenz law, the induced current will try to decrease the magnetic field. So initial direction of magnetic field is into the plane. So due to induced current, direction of magnetic field will be out of the plane. That will be the anti-clockwise direction. You know, if you in the coil, if you have anti-clockwise direction, then magnetic field inside will be outward. So in this case, the direction will be anti-clockwise. Now the third case, suppose that this loop is going out. So now inside we have maximum flux, and then now is going to flux equal to 0. So now flux is here decreasing. So now you can see the changes. The important point is now flux is changing. Then you can see the here induced current. So now induced current will try to support the magnetic field, because magnetic field in a flux is decreasing. So initial direction of magnetic field is inside the plane. So in this case we have clockwise direction. So direction of magnetic field will be clockwise. So inside the field, inside the loop, you can direction of magnetic field will be downward, that is supporting to initial value. Okay, let's see the another example. If you have a one coil here, okay, and another coaxial coil, okay, and the current is a, in this coil we have current here I1, okay, and loop is a, this loop is a moving with some constant velocity v. So the case first, loop is a coming closer, it means flux is a increasing, okay. So the induced current in the loop will try to oppose the increase. So the see the what is the direction of magnetic field here. So direction of magnetic field, so in this case suppose that if you have here is given anti-clockwise direction, in this given the I, okay, and you have to find out here what is the induced current in this coil, okay. So okay, so the first case, when loop is a coming closer, so flux is increasing, so induced current in the loop will try to oppose the increase. So where is a direction of magnetic flux? So you can see in here is anti-clockwise direction. So this is anti-clockwise direction. So direction of magnetic field will be in this, and then flux is increasing. So induced current will try to reduce the magnetic field. So this will be the anti-clockwise here. So that in this there will be current in the anti-clockwise, and you know the if you have a current carrying here I, what is the direction of magnetic field? So you can use the right hand thumb rule. Right hand thumb rule. So put the thumb in the direction of current and your curl the forefinger, and forefinger will give you the direction of magnetic field. Second, when the loop is going away, okay, so when loop is going away, then flux is decreasing, then current will in the coil will be clockwise, because in the clockwise then it will try to support the initial direction of flux. Okay, let's see the another example. Suppose that if you have a coil, okay, and one here you have bar magnet. This side is a given south pole, this side is a north pole, okay. So and this bar magnet is a coming closer to the loop. So it means flux is a increasing. But now you can see here direction of magnetic field will be in this direction, because this is the south pole. This is an important point. If you have north, then magnetic field will be in this direction. So now you have south, so the direction will be here. But flux is increasing, so due to induced current, magnetic field should be in this direction. So how to? So if you have a clockwise direction, so I will be clockwise, then you can see the magnetic field will be in this direction due to current carrying coil. Second case, when this coil is going away, okay, direction of magnetic field will be same, but flux is decreasing. So flux will decrease, it means current you have to select in the coil that going to support the magnetic field. So in this direction you have initial magnetic field. So the direction of current, this is anti-clockwise direction. So anti-clockwise. Let's discuss the another example. Suppose that a bar magnet dropped just above the current carrying loop. So this is the current carrying loop you have. This is a direction of current I. Okay. Now one magnet is a drop from the just above the loop, and this is the north and this is the south. Now the question is what is the acceleration of the magnet bar? First case, A is equal to G. First option is given A is greater than G, and third option is given A is less than G. In the both the cases, when this bar magnet is coming from the top and after going also. Okay, so let's discuss in the all two cases. So you know, if you have a north, then magnetic line will go like this away. Okay, so when approaching the first case, case 1, so bar magnet is approaching, that time flux is increasing in this coil. So flux will increase, okay, and then induced current will flow in this coil, and direction of induced current will be try to oppose the magnetic field. So of course this is the anti-clockwise direction. You know, the coil is also called equivalent to the bar magnet, and if you have an anti-clockwise direction, then you can make here one bar magnet, that is here north to south, because direction of magnetic field inside the bar magnet will be south to north. And in the coil also, if you have anti-clockwise direction current, then magnetic field inside the coil will be upward. This is this way. Okay. So now suppose that magnet was coming, this is the north pole and south. After induce, the coil behaves like a bar magnet, and that is this side will be north and this side will be south. So you can see north if you have it same, then it will repulsion will happen, and acceleration here will be less than G. Now go to the second case, when bar magnet going away from this. So this you have south and this you have north. So the magnetic flux is decreasing. So magnetic flux will decrease, and then current in this coil will be clockwise. So if you have a clockwise, then you can write equivalent magnet bar will be south and this is the north, and this is the you have south and north. So now you can see there is attraction here, attraction between the coil and bar magnet. So again acceleration is going to less than G. So when bar magnet dropped above the current carrying loop, okay, so in this case acceleration of the bar magnet will be less than G. Okay, let's discuss the another question. So you have one coil here. So the radius of the coil is given B. There is some another small coil here, loop is given, that is radius is A, and given this A is much less than radius of B. Okay, and the first coil current is changing with respect to time. So the I is given I naught into T. So the find the current in the smaller loop. This is the question you have. So as we know, when current is changing in this loop, then first you have to calculate the flux through a smaller loop. Okay, and you know the formula of the flux, that is AB cos theta. What about the area? Area will be pi A square. What about the magnetic field at the center of the coil? That is mu naught. I is given I naught into T by 2B. Okay, and now you can see the angle is a 0 degree, theta equal to 0 degree. Okay, so what about the EMF? EMF will be d phi by dt. I am taking mod here because we always find current by using the Lenz's law. So the d phi by dt, so pi A square mu naught I naught by 2B. Okay, so the current will be E by R, that is a mu naught pi a square I naught by BR. Okay. So what is the direction of current in the smaller loop? That is also important point. So see, if current is a in the, what is the initial direction? Initial direction of magnetic field is a outward, so denoted by dot. Okay, and flux is a increasing, because you can see I is a I naught t. So in time will increase, the current will increase, the flux will also increase. So due to induced current, always they are going to oppose the initial magnetic field. So inside the field, direction of magnetic field should be into the plane. So into the plane, it means it should be the clockwise. So the direction of current in a smaller loop will be clockwise. Okay, let's discuss the another question. Suppose that you have one wire, carrying wire I equal to I naught into T, and you have one loop. Okay, this is a square loop is given, length is a L. Okay, find the induced current through this coil. Okay, current and direction both. Suppose that R is a given the resistance. So flux. So here you can see the magnetic field in the coil is going to vary, not uniform. So first important point is a magnetic field is not uniform. If you don't have uniform magnetic field, then you should take one element here. So I am taking one element. First cut is after x distance, and then x plus delta x. So this thickness is a delta x. So now magnetic field at this point is a B at x equal to mu naught I 2 pi x. Okay, so then the flux through this small strip, that is a L into dx, will be the area into magnetic field mu naught I 2 pi x. So just integrate. So you have to integrate from A to, this distance is given A, so A to A plus L. Okay, so now you can write here mu naught I is given I naught T, okay, into L by 2 pi into dx by x, so that will be the ln x, and A to A plus L. So the flux equal to mu naught L by 2 pi ln A plus L by A into I naught into T. Okay, so now you have flux. So you know the current equal to d phi by dt. So you can write here flux equal to, all term is a constant, exactly k into T. So the d phi by dt will be k, and if your resistance is R, so the current will be k by R. So answer will be mu naught L by 2 pi ln A plus L by A I naught by R. Now what is the direction of current? Because here is saying current is increasing, it means magnetic field is going to increase. So magnetic field will increase. So the magnetic field inside the loop due to induced current will be opposed the initial direction. So what is the original direction of magnetic field? Into the plane. So denoted by cross. So due to induced current, it must be dot. Okay. So direction of current will be anti-clockwise, like A, B, C, D. I am just writing here A, B, C and D. So direction will be A, B, C, D. A, B, C, D. Okay.